Hello everyone. As promised, I'm gonna move on with basic videos on vibrations just to make my playlist vibrations complete. So in this video, we're gonna look at free vibrations of undamped single DOF systems. So systems with only 1 degree of freedom. And we're gonna look at free vibrations without damping. That's kind of the simplest kind of vibration problem you can possibly get. And so we start with a bunch of examples. So I have 5 examples, I guess, right? Yes, 5 to 6 examples, actually. 6 examples, and I'm going to show you a bunch of problems. So we start with one of the simplest ones, which is a pendulum with the mass concentrated at the end. And here I want to tell you what undamped mean, what is a free vibration is versus forced vibration, which we're going to see later. So here we have a pendulum with length L, mass M concentrated at the end. The degree of freedom of the system is theta, deviation from vertical degree. There could be an external torque here at the joint, or there could be no external torque. And there could be some damping here, okay, which is a kind of backward torque that is going to slow down the system. That is because this joint here could be lubricated and could have viscous friction or Coulombic friction. Now, most of the times we look at viscous frictions, which is what you're going to see in my next video, where the torque here is proportional to the angular velocity theta dot times a constant c, which is called the damping constant. And that is due to the lubrication of that joint, and that is going to slow the system down. So we can have these or not. In this example, I'm not going to have any of them. So my system is not going to have any damping, anything that will take away the mechanical energy of the system and slow it down to ultimately make it stop. And I will have no external forcing that injects energy into the system. So how does the system vibrate? Well, all I do, I move it away from the initial position, from the static equilibrium position, which is perfectly vertical. I move it away, I give it some initial angle, or if it's here, I give it an initial kick. Basically, I give it an initial angular velocity, or I can do both. I can bring it to some non-zero angle and give it a kick and let it go. Anyways, this only way that you make the system vibrate is under non-zero initial condition. So let's take a look here. So for the moment, I assume that there is no external torque and the damping coefficient is also 0. So no damping and free vibration. So if I take some of the moment about the pivot point, the only 2 forces that I have are the tension in the rope and the mg. Now tension in the rope passes through point O, has no moment about it or torque. mg has 2 components, mg sine and mg cosine. Sine one is perpendicular to the rope, the cosine one is along the rope, and so that cosine component will also have no moment about point O, so only mg sine does, and the moment of it is mg sine, the force, times what? Times the distance L. And if you see, the way that the angle is increasing is counterclockwise, okay? So the angle is increasing from 0 to non-zero counterclockwise, but the moment of this mg sine is clockwise, right? Therefore, the moment is going to be negative mg L sine theta, and this is equal to the polar moment about point O times theta double dot, or alpha angular acceleration. Now, if the mass is concentrated at the end and the rope has no mass, then the polar moment of this mass about the point O is simply mass times distance squared. So it's going to be ml squared. And from both sides, you can get rid of one n and one l. And your equation is going to be theta double dot plus g over L sine theta equals 0. Now, another way that you can say the system has free vibration is look at the governing differential equation of the system. If you look here, the left-hand side has all of the dependent variable theta. On the right-hand side, there is no function of time. So f of t here, the right-hand side is 0. Okay, therefore, if you have a solution to this differential equation, you know in general it has 2 solutions. a homogeneous solution and a particular solution. The particular solution is due to the forcing function f of t, which in this case you don't have. So all you have is a homogeneous solution. Your forcing function is 0, and the homogeneous solution, as I said, is only due to initial conditions that are non-zero. If they are 0 as well, then theta is going to stay at 0 all the time. So when your only solution is the homogeneous solution, you have free vibrations. Okay? Right? So this is the definition of free vibration, no forcing function. The system only acts due to initial condition, and that is what we are going to see later, how we apply initial condition and we get the final response. Okay? So, and the system clearly has one DOF. Now, that's one way to derive the equation of motion using Newton and Newton-Euler, or we can use the Euler-Lagrange method. You can use this method that is more suitable for systems with more DOFs. In this case, we have to formulate kinetic energy. Now, this object has only a point mass, so the only kinetic energy is a translational one, 1/2 mv squared. And since the particle m is going around on a circle around point O, so when an object has a circular motion, if you remember, v equals r omega, right? When you have a circular motion, r is the radial distance from the center, and omega is the angular velocity. In this case, r is equal to the L. Omega is the same as theta dot, so your velocity v is going to be L theta dot for this, right? So in this case, when the object moves in this direction, this velocity here that the object has and is perpendicular to that rope, that is equal to L times what? Theta dot. So that is going to be the kinetic energy. Now, potential energy is measured from a datum. So you need to have a datum in this case. For that, let me do a little bit cleanup here so I can show you how I got the potential energy. And then we are going to go from there, okay? So for potential energy, you have to have a datum. And here I consider my datum where this mass comes at the very bottom of it. Okay, the lowest point, the lowest elevation, because you know, potential is measured with elevation due to gravity. So here I put that as the datum of my potential energy. So the potential energy here is this elevation, whatever it is, how much I moved up from the datum times mg. So mg times this distance is my potential energy. Now, how much is it? If you look at this distance, so it is basically the difference between this distance and this one. Now, that big distance is the same as L. And this one, if you look at this right triangle, this is L, that is theta, that is L cosine theta. So that height here is L minus L cosine theta, which you have over here. And times mg, that's the potential of gravity. Then Lagrangian is kinetic minus potential, so it is going to be this. Now you have to find two partial derivatives. One is partial of L with respect to theta, one with respect to theta dot. And partial of L with respect to theta only comes from this negative mg negative L cosine theta. Those negatives would cancel. And derivative of mg L cosine theta is going to be negative mg L sine theta. And then derivative of this with respect to theta dot is only this term, which is going to be ml squared theta dot. Then the Euler-Lagrange equation is d over dt of partial with respect to theta dot minus partial with respect to theta is equal to any generalized force torque that is non-conservative. Now, in this case, again, because the external force is, which is non-conservative, external torque, which is non-conservative, is 0, and as I said, the damping, this guy here, that was c theta dot, that is also 0 in this case, then this is all 0. If they were not 0, you have to add them. So it would be T external in this case minus C theta dot if they were not 0. And if you plug them in, what would you get? Well, partial of L with respect to theta is this. Taking time derivative, you get ml squared theta double dot. And then minus this. So this is a minus, this is another minus. They cancel each other. So you get plus mgl sine theta equals 0 if they are both 0. If not, then you will get a function which is t external minus c theta dot. You see? Then it's not going to be a free vibration. It's going to be forced vibration. Guess what? Because you have a function of time here. It could be even constant, but still there is a forcing function, non-zero forcing function. This guy, you can bring it to the other side, and that is your damping. So if you have this is going to be forced vibration and with viscous damping, which is what I'm going to show you in 2 videos from now. How to do that. In this case, we set both of them to 0. So my equation, again, if I simplify 1m and 1l, is going to be the exact same thing as I got with Newton method. So whether you use Newton method or whether you use the Euler-Lagrange method, the ODE, the differential equation, should be the same. You should not get a different one, okay? And you see you don't. Now, this ODE is clearly a nonlinear ODE. You have sine of theta, and theta of t is the one that you need, the dependent variable. So that's a nonlinear. And guess what? This guy has no analytic solution. So if I give you 2 initial conditions, like theta 0 and theta dot of 0, and say, hey, could you find for me the answer? Guess what? You cannot find the answer. There is no answer. Nobody so far until this very day could solve ever this differential equation. Okay, and there is even proof that you cannot do it. It leads to a second elliptic integral. There is no solution for that. The only solution for this is a numerical solution. So if we want to get any analytic solution, we have to linearize this ODE. And the way that you can do it, which is very common in most of the books and so on, is what we call the small angle assumption. So we assume that this total deviation, the theta, is going to be a small angle. Now, what is small? What's the meaning of small here? Small, you know, many textbooks say, hey, it's much less than 1 radian. Well, how much less? Typically, when the angle is below 6 degrees, if you plot the sine function, so if you plot the sine function, so this is sine theta, and you look for, and remember this guy here is 180. So if you come down and zoom in to about 6 degrees, go in and zoom in to about somewhere like, let's see if I can even draw here, to something like 6 degrees. Of course, that's still way bigger than 6 degrees. You see that if you plot the line f of theta equal theta, then that line and that sine function almost are on the top of each other for the first 5-6 degrees. Okay, so I can approximate my sine function by what? By the theta itself. And you can just look at it in MATLAB or any other software. You can pass the values of 1 to 6 degrees, 1 to 5, 6 degrees, and compare the sine of the function to the sine of theta to the theta. The only thing is when you say these two are equal, pay attention that this theta has to be in radians, not in degrees. So you cannot just say 6 equals sine of theta. No, that 6 has to be converted to radians and compared against sine of 6 degrees, and then you'll see whether they are equal or not, or it's a very good approximation. So if the angle is less than typically 6 degrees or so, you can approximate sine theta by theta, and cosine theta is almost 1. So you can use these two approximations in linear vibrations, right? Where you linearized your ODE, you replace this sine theta by theta, so now your ODE is this simple guy. Now, clearly, it's a second order linear ODE with constant coefficient of 1 and g over L, and is homogeneous. So the solution is extremely Simple. But before that, let me first show you those angles that I mentioned, right? 1, 2, 3, 4, 5, 6 degrees. See if that approximation is any good or not. So here is MATLAB, and I say, what is sine d of 6 or 4 or 5? Let's just pick an angle. So that is sine of 3 degrees. Now, if I convert 3 degrees to radians, I need to multiply by pi, divide by 180, and look at those. You see? They are the same to the 3 decimals. The 4th decimal, there is just one difference. And if I go to 4 or 5 or anything, I can see the same thing. Now, let me do something. So here I do sine d of 1, and then 2, and then 3, okay? And then I repeat that for 5 and 6, 4, 5, and 6. So let's see all of them in one place, and then minus. Now here I do 1 and 2 and 3, 4 and 5 and 6, and multiply them by pi, divide them by 180. So I want to subtract sine of theta minus theta. So you see the numbers, and look at the numbers. This guy is 10 to the negative 6 or 7. This guy is 10 to the negative 6. This is that. This is that. You see, they're all below 10 to the negative 3. Look at them. Okay? It's relatively good. Or if you want, you can, again, plot theta and sine theta, right? So say theta equals, for instance, 0 to, I don't know, 30 degrees, correct? And then say what? Say F1 equals sine d of theta, correct? And now you can say plot theta and, of course, theta, except theta times pi over 180. And let's do this in blue. So this is going to be your theta function, right, in radians. And then I'm going to do a hold on. And then I'm going to plot for you theta versus F1, which is sine of the function, and do this in red. So let's take a look now. You see, here are these two functions for the first 30 degrees. And if you look here up to 5, 6, even 7 degrees, you can see that the two curves are very, very close to each other. Okay, so here is a better zoom. You see, it's about 6 degrees that they start, even if I zoom in further, they start to kind of separate. You see that? Look. Now, this area that you see the separation is now relatively visible. Again, you can zoom in further if you want. And you see that, you see still up to 6 is not bad. After that, they start separating a little bit. So typically up to 5 or 6 degrees, people say that the depending on your accuracy, it's a good approximation. Okay, so going back to the differential equation, it's a, as I said, homogeneous second order ODE with constant coefficients. The way you solve it, you form the characteristic equation. In this case, s squared plus GL over L is 0. The roots are two complex numbers. That means the solution is going to be a combination of a sine and a cosine of what? Of omega nt. What is omega n? In this case, omega n is going to be this guy here. So if I call this omega n, my roots are plus minus I omega n. Then my solution is a sine omega n plus what? B cosine omega n. And in this case, omega n is, as I said, the square root of G over L. And this guy, I call it the natural frequency of the system. Why? Because look at my solution. My solution is a harmonic oscillation where the frequency of my oscillation of the system is omega n, this guy. So I can call it the natural frequency of the system. Why do I call it natural? Because this is the response of the system to only initial conditions. There is no external force with its own frequency to affect how the system is going to oscillate. You'll see in my video, that is 2 videos from now, when I talk about force vibration, you'll see that if this T external is a function like, for instance, T times sine of some other omega T, then you'll see that you will have, as I said, a particular response. Your theta is going to be theta homogeneous plus theta particular. This theta particular is not going to be in omega nt. It's not going to be sine of omega nt. Actually, this homogeneous one will be, but this particular one is going to be of type sine this other omega times t. So the particular solution will be of the input frequency, not the natural frequency of the system. And you're going to see 2 frequencies in the system. Okay? We'll talk about that. So the natural frequency of the system here is, in this case, square root g over L. And my only solution, which is homogeneous solution, is going to be the combination of those. Another way some people write it is, they write it as a simple sine function plus a phase and a modified amplitude. So they write it like x times sine of omega nt plus phi. That is very also common in books. In that case, that x, that total amplitude, in terms of what I wrote here, is going to be square root of a squared plus b squared. And that phase phi is going to be tangent inverse of a over b. Okay, so you can combine a sine and a cosine and write it as a single sine with extra phase and modified amplitude. So you can write it both ways. So here my unknowns are a and b. In that case, my unknowns are going to be x and phi. You can do either one, no difference. Okay, the answers are the same. So now that I have 2 unknowns to find, these 2 unknowns come from the 2 initial conditions. I can give my system an initial angle, and I can give it an initial angular velocity or initial kick, or I can give both of them. So what are a and b in terms of these? Well, all I need is to plug 0 in this solution. The sine will go to 0, cosine will be 1, so you only get b. B is going to be theta naught. And then if I take time derivative of that and set it to 0, well, guess what? The time derivative of this sine will be a cosine, and this guy is going to be a negative sine. Now, negative sine at t of 0 will be 0, cosine will be 1, so you get just a, except when you take derivative of sine omega nt, that omega n comes out. So you get a omega n. That is equal to theta naught, theta dot naught, or theta dot 0. And so that's your b. A is going to be theta dot naught over omega n. So that is a. And this is b. So your solution is this solution in this case. This is how theta is going to behave if it's small. It's going to be something related to sine and something cosine. Now, if you just release the system from rest and theta dot 0 is 0, then this term is going to be 0. You get a pure cosine response. If your initial angle is 0, but your initial angular velocity is non-zero, you're going to get only a sine response. And if you have both of them, you're going to get both sine and cosine in the response. Now, what kind of response is that? If you plot it, clearly the sine and cosine are functions that will show oscillations forever. So in this case, your initial angle is your initial value, right? So this is theta versus time. If you plot it, your initial value is theta naught, and your initial slope here is basically theta dot 0. So you're going to get something like this, right? Let's say, okay? So you're going to get this kind of response where this initial slope is theta dot 0 and initial angle is theta 0. And clearly this is a sustained oscillation, which means the pendulum keeps oscillating forever. Now, you know, in reality, nothing oscillates forever. Why? Because there is always a damping. There is always a damping, which we'll see in the next video. It will kill out the energy of the system and convert it to heat or sound or both. Unless I have a battery that keeps injecting some external torque into the system to keep that pendulum on your clock keep going back and forth. Okay, so we're going to see all of that. But remember that in this case, we assume that no torque, no damping, so the system shows sustained oscillation. Okay, this is very theoretical, but that's the solution. Now, that was the first system. You might say, what if the pendulum has distributed mass? So the mass of the pendulum is not concentrated at the end. The whole pendulum has mass, which is more realistic. The centroid of it, and it's not perfectly symmetric, so the shape of the pendulum is not like a simple slender bar. The centroid, if the whole distance is L, the distance of centroid to the pivot point is D, and D is not necessarily L over 2. And in this case, right, what is the equation of motion? In this case, still it's the same. Again, if you draw FBD, you have mg and you have the two pin forces. The pin forces have no moment about mg does, and mg, again, remember there is mg sine and mg cosine. This cosine has nothing. Mg sine does, except this mg sine this time should be multiplied by distance d. And of course, again, for the counterclockwise theta, the moment of this is negative. So you get negative mg, right? So that is mg sine theta. You multiply that by d with the negative sign, that's your torque, equals I or j, whatever you want to call it, about O times theta double dot. Now this I does not need to be anything special, right? Because if it's a slender bar, if this guy is a slender bar that you see in many books with mass m and length L, that is a special case, and the centroid is exactly here in the middle. In that case, your D is L over 2, and the I about 0.0 is going to be ml squared over 3. Okay, but in general, that I about 0.0 could come from the mass distribution within this pendulum, and it could be just a given parameter, which can come from a CAD model or something. So in general, the governing ODE, if you simplify, is going to be like this, assuming, again, you have a small angle. So the sine theta is replaced by theta, then your governing ODE is going to be this guy. Theta double dot plus mg d over I naught equals what? Times theta equals 0. Again, second order linear ODE, and it's homogeneous. Okay? Now, as I said, if it's a slender bar, then you'll get what? You get mg, that d is going to be L over 2. I is going to be ml squared over 3. If you simplify, guess what? You're going to get 3g over 2l. Remember, for the regular pendulum, this coefficient was simply g over L. If it's a slender bar, you're going to get 3g over 2L. Okay, if it's a slender bar. If it's not a slender bar, then you simply get this one. Now, you can also, again, derive the equation of motion instead of Newton method. You can use the Euler-Lagrangian. This time, you have a rigid body. And a rigid body has two kinetic energies, one due to translation and the other one is rotation. So your translation term is 1/2 mass velocity at the centroid squared. Your rotational term is 1/2 I about the centroid times theta dot squared. And this is for a 2D case. For 3D case, this guy is going to be written as omega transpose I is going to be a 3×3 matrix times omega. Okay, so if you want to know more about Euler-Lagrange method, I have several videos under my playlist dynamics, and you can learn all about Euler-Lagrange. I probably copy-paste those videos into the vibration playlist for you so that you have a good reference. when you want to learn about Euler-Lagrange, you have those videos under the same playlist. Okay, so I'm going to copy paste them for you. Now, velocity of the centroid in this case is clearly, again, because centroid is going on a circle about point O, the velocity of it, v, is going to be r times omega, which r, in this case, r is d. So velocity of the centroid, this velocity here, is going to be d times theta dot. And that is what I'm going to replace here. I about centroid and theta dot squared. So if you write it and factor out theta dot squared, you're going to get this. Now, if you look at this guy here, this is parallel axis theorem. I about centroid plus md squared, and d is the distance between centroid and the pivot point. So I can say that whole thing is basically I about the pivot point. So your whole kinetic energy is going to be 1/2 IO about IO times theta dot squared. And that makes sense. Why? Because you can say my entire rigid body is actually doing a pure rotation about pivot point. So I can say it only has one rotational kinetic energy, 1/2 I theta dot squared, but I should be about that pivot point, not about centroid anymore. So you can do that as well. Potential energy, very similar to last time. It's mgd minus d cosine theta, because now your centroid is d units away from the pivot, not L units. Okay, so it's going to be d minus d cosine theta. Okay, just refer back to this logic that I used for you and show that this distance was L minus L cosine theta. This time your centroid is here, so you have d and d cosine theta. And so this is going to be the difference between them, which is what you can see over here. So you subtract these two, you get the Lagrangian, find the partials with respect to theta and theta dot, plug them into the Euler-Lagrange equation. Again, in this case, I don't have any external torque or damping, so the non-conservative generalized torque is 0. If you plug this term here and simplify, you get the exact same ODE that you got with the Newton method. If you just go back and look at this one, you see these two are the exact same thing. All you need is to divide both sides by I naught. And in this case, of course, replace sine theta by theta because you assume the angle is small. So clearly you get the same equation. Now, if somebody says, what is the natural frequency in this system? What would you say? You are right. If I want to solve this, I need to find the characteristic equation, which is s squared plus mgd over I naught equals 0. And if I solve for that, let me do a little bit cleanup here. If I solve for the roots, you see that the roots are what? S1 and 2. They are plus minus I times square root of mgd over I naught. So this guy is your what? This guy is your natural frequency in this system. Okay, mgd over I naught square root. Again, if it was a slender bar, it's going to be the square root of this. That is going to be your natural frequency. Okay, so that's the second example. Let's go for a third example. Again, very, very common example. One of the first examples that you see in any vibrations book is a mass spring system. So here you have a mass on a rolling support that there is no basically friction here. There is no Coulombic friction. It's just rolling without slipping. So if you draw the FBD of the object, the only force is K times X. And X here is the deflection from the unstretched length of the spring. Okay, so at X of 0, the spring is unstretched. Okay. When X is not 0, then X is the elongation of the spring, so it is applying a force kx in the opposite direction. You know, when you pull a spring, it is going to pull back. And you also have mg and n. Again, there is no kinetic friction. Now in the x direction, the only force acting is kx in the negative of x, right? Because positive x is to the right, this force is to the left. So if you write the Newton equation, sum fx equals 0, sum fx equal max, ax is x double dot, and some force in the x is negative kx. So bring this guy to the other side, divide by a m, and this is your governing equation. Again, second order linear ODE with constant coefficients, very similar to the pendulum, right? So that is your governing equation. Similarly, you can use Euler-Lagrange. Kinetic energy is 1/2 mv squared. V is x dot in this case. Potential energy, there is no potential due to gravity because the object moves on a flat surface. The only potential you have is the spring, and the potential in a spring is 1/2 kx squared, where x is the deflection. So Lagrangian is the subtraction of the two. You find the partials of L with respect to x and x dot. Partial of L with respect to x is negative kx. Partial of that with respect to x dot is mx dot. Plug it into the Euler-Lagrange equation. This is going to be mx double dot minus kx. You're going to get positive kx, and this is your governing ODE, which is the exact same thing as this if you just divide both sides by m. So it doesn't matter which method you use. You can also use work energy method, which is very similar to Lagrange, and the governing ODE is the same. Okay? Now, again, if you want to solve, you have to find the characteristic root, which in this case is s squared plus k over m is 0. So you see the solutions are plus minus I times square root k over m. So again, this square root k over m is going to be your natural frequency. And your solution, which is only a homogeneous solution, is going to be a sine omega nt plus b cosine omega nt. And again, a and b are coming from the initial condition. You can initially move the spring away from static equilibrium and let it move so it keeps oscillating back and forth. Or you can give it an initial velocity by kicking it, or you can have both. In this case, again, you can find B and A based on these two initial conditions, and this is, again, a sustained oscillation for the system. So it keeps going back and forth, until what? Until it basically stops. But does it stop in this case? No. Why? Because there is no damping. Since there is no damping, none of these functions will ever stop. So as I said, you get sustained oscillation. There is nothing to eat away the energy of the system. And there is nothing to inject energy into the system, so the amplitude will not change. It's not going to increase, it's not going to go down, because there is no non-conservative force in the system. If it was, depending on whether they inject energy or they eat away the energy, you'll see the amplitude of the oscillation to get bigger or smaller. In this case, the amplitude of the oscillation is not going to change. In fact, if somebody says, what is the amplitude of the oscillation here? You go back to this formula that I just showed you above, that you have to square a squared and b squared and take a square root of that. So if somebody says, if I have both x0 and x dot 0, none of them is 0, what is the amplitude in this case? You say the amplitude x is square root of this guy squared plus what? This guy squared. That is the amplitude of this kind of oscillation. What's the frequency of the oscillation? That's the natural frequency. What's the phase? If you want to write it as a phase, it is going to be tangent inverse of the sine coefficient over the cosine coefficient. The sine coefficient is this x dot 0 over omega n, and the cosine coefficient is x0. So you can also write it here. You can write that whole thing as x times sine of omega nt plus phi where x and phi are coming from these two formulas. Okay, but again, the response is, as I said, what it is: sustained oscillation. Okay, good. So this is about these three simple systems: pendulum with concentrated mass, with distributed mass, and the mass spring system with nothing else. Now here I want to show you a couple of more advanced examples for single DOF systems that can be more interesting to you. So one is, many times we can use this formula that we just derived, that for a system with some stiffness and with some inertia or mass, we can use this formula, omega n equals square root of k over m, if k is what we call equivalent k, or equivalent stiffness, and the mass is equivalent mass of the system, we should still be able to use this formula. Well, how? What is equivalent mass? What is equivalent stiffness? How do we use it? For instance, I give you this system, which is a cantilevered beam and a mass on it. And you know, if you put the mass here on this cantilevered beam and make this guy go down and let it oscillate, this system will have some frequency, right? What is the natural frequency of this system? Well, you might say, what kind of relation exists, what kind of similarity exists between this system and this mass spring that you just showed me? Are these two any similar, so I want to use the same formula for both of them? The answer is yes. Both of them have a mass and both of them have a spring. In this case, the spring is this basically tensile or compressive spring, right? So it applies a force when you stretch it or compress it. In this case, your spring comes from this cantilevered beam, where it shows stiffness, it shows resistance when you deflect it laterally. And depending on where you deflected, where your mass is it at the end, is it in the middle, where it shows different amount of resistance and stiffness. So if you look at your vibrations book, in this case, by the way, all of our material is coming from the amazing book Theory of Vibrations and Application with Thompson et al. Actually, it's not just Thompson. There are two other authors on this book. So I get my pictures from this book. If you go and look at it, you look at the book. In the book, there is a table which has equivalent stiffnesses for different kind of objects. For instance, it says, hey, if you have a cantilever beam with length L, with Young modulus E, and with the second moment of inertia I, the stiffness K for it, if you move the end of it, is 3EI over L cubed. If it's a simply supported beam and you put your mass or anything, deflect the center of it, this is the stiffness for it. If it's a beam that has both fixed ends, this is the K for it. If it's cantilevered with a simple support, that's this one, right? And so on and so forth. If it's simple support and you put it off center, that is this one. If you have, for instance, a kind of vertical, horizontal plane that is on a vertical, again, cantilevered beam, you can have this K. And there are also, if there is something here, right, with an overhang, if you have a torsional spring, if you have springs in series or in parallel, it gave you an equivalent K for different scenarios, okay? Now, where does it get these from? For instance, just let's look at this scenario here, the one that we are dealing with. Where would you get that K from? Here, you have to look into solid mechanics. If you remember from solid mechanics, if I have a cantilever beam and I put a load P at this end and the length is L, the material is E, and the geometry is I, it goes down And the amount of this deflection delta at the end, if you remember, this delta from solid mechanics is PL cubed over 3EI. If you don't know where this one comes from, look at my solid mechanics playlist videos and you'll find it, where I have a video on deflection of the beams, calculating deflection of the beams, and I did this. Okay, now what does it have to do with K equivalent? Well, what is K in this system? What is K? K is defined as what? Is defined as the force that your system, if you look at it, K is, let me clean up a little bit. K is what? Is the ratio between the force of the spring and the deflection of the spring. So this X is the same as delta for this spring. That's how much this spring is being stretched or compressed. So this K is the spring force over the elongation of the spring, right? This stiffness of the, or the constant of the spring. So here I can define a similar thing and say delta, if delta is that, I can say K in this K, or K equivalent, is the force P over the deflection delta. Well, if I plug in the formula for delta, right, what would you get? These two would cancel. You get 3EI over what? Over L cubed. That is exactly this. Look. So that is how you can find an equivalent stiffness. In this case, similar. If you look at solid mechanics, if you want to know the deflection of the simply supported beam in the middle, this deflection here for this case, right? This deflection delta should have been what? Should have been basically the force P. If you apply a force P here, and that is delta, that should be P over that K. So if you look at solid mechanics, you should have something like PL cubed over what? Over 48 EI. So when you divide that P by that delta, the K is what? The K is this guy. So if you look at solid mechanics book, you should have this, and so on and so forth. Now, what about a parallel or a series of springs? How would you get those formulas from? So let me show you those, because they are very useful and important. And then we're going to go back to the two examples. So how would you get this? So if we have two in parallel, okay, if I apply a force F here, yes, and like force F1 and a force F2, or let's say in this case we fix one end of them to the wall to make it even simpler. So if I apply a force F here, good, you know that because these two are attached to these two fixed plates, their elongation, if you call them delta 1 and delta 2, the delta 1 and 2 should be the same. Otherwise, these two plates will not stay vertical. So in this case, delta 1 should be the same as delta 2. Yes? And that should be the total delta if you replace that with one single equivalent K. So if you say that, I replace it with one equivalent K, where if I apply this force F to it, it gives me the same delta. Now, what relation exists between this K equivalent and K1 and K2? Well, this is the relation between their displacements. What about the forces? Well, each one of these springs is applying some force to these plates. So if you draw the free body diagram of this plate, you see that on one side you have the total force F. On the other side, each one of these springs is applying their own force. So there is F1 and there is F2. Now, if the mass of this plate is negligible, so assume that this M is very close to 0, it's just an imaginary plane, a very thin plane or plate, then clearly F1 should be the same as F should be the same as F1 plus F2. Now what is F? F is K equivalent times delta, based on what we learned. F1 should be what? Should be K1 times delta 1, and F2 should be K2 times delta 2. Now remember, the deltas are all the same, so I can get rid of them. And guess what? You get K equivalent is K1 plus K2, and that is exactly this. Okay, so two springs in parallel, the equivalent is sum of the two. Or if you have 3 or 4, it's just sum of them. Now, if it's series, you have the reciprocal formula. Where does that come from? So let me show you that one very fast as well. So here, again, to make life easy, I apply a fixed end here, and I pull this with force F, right? And I say this is equivalent to, again, one single spring fixed at one end and the same force. They have to show me the same delta. Okay, so the delta that you get out of both of these should be the delta that you get out of this. So in this case, this F equals delta K equivalent. In this case, what? Now, in this case, the force F that you apply to the end of the first spring is not going to be applied here as well. Okay? Or is it? Well, for that, we need to look at the free body diagram. So if you look at the free body diagram of this first spring, there is some force F here, and there is some force F1 from the other spring. Now here, we assume again that the mass of the spring is negligible. If that's the case, F should be the same as what? F1. And if you look at the other one, this side is F1, this side is F2. Again, if you say that M2 is 0, these are not heavy springs, then F1 should also be the same as F2. So in this case, you see that for these scenarios, F, the force in each one of the springs, is the same. They are all equal to the external force, but not their elongations. Why not? Because they have different Ks. When you have equal forces and different stiffness, their deflections are going to be different. So this guy has deflection delta 1, this guy has deflection delta 2. Delta 2 is measured from the wall, delta 1 is measured from delta 2. So your total delta in this case is equal to delta 1 plus delta 2. So if I write it here, in this case, the total delta, right, is going to be the same as delta 1 plus delta 2. Sorry. So let's write it down. And delta is clearly F over K equivalent. And delta 1 is F1 over K1, and delta 2 is F2 over K2. But remember, we said that the F's are the same. F is the same as F1, and F1 is the same as F2. So we can go ahead and get rid of the F's. So here, and that's your relation. 1 over K equivalent in 1 over K1 plus 1 over K2. Or if you simplify it, you can see that K equivalent is going to be K1, K2 over K1 plus K2. Just take a common denominator and take reciprocal. And that is exactly this formula here. Okay, so these are equivalent scenarios for different systems. Of course, there could be a lot more than that, but these are some simple scenarios. Now, if I come back and look at these two examples with equivalent mass spring, So in this system, the mass is on a cantilever beam with deflection at the end. So I need to find the K equivalent from this diagram, which is 3EI over L cubed. The mass is this total mass, and square root of K over M is omega, natural frequency. So this is going to be what? The natural frequency of this system, just like that. Very simple. What about this guy here? So here I have K1 and K2 in parallel, K3 is attached to them in series, and M, and I want the natural frequency in this. So if I replace these three with a single K equivalent and mass, I can show that it is going to be, again, square root of K equivalent over M. What is K equivalent? Well, first I replace these two with an equivalent, which is simply going to be K1 plus K2 because they are parallel. And then that guy with K3 is in series. So now I have to use that other formula, this one that we just learned. And if I do that, your K equivalent is going to be K1 plus K2, the whole thing times K3, and then K1 plus K2, the whole thing plus K3. That is my K equivalent divided by M under a square root. That is your natural frequency of the system. Okay, so for different scenarios, if they give you this or anything else, if it's just a spring and mass, you can use the formula square root K over M, as long as K is the equivalent K. Now, one thing that I need to emphasize here is, you might say in this case, the spring mass system is vertical, it's not horizontal like this. Well, what's the difference? The difference is mg. In this case, mg plays no role in lateral deflection or horizontal deflection of the spring. They are perpendicular to each other. But in this case, mg, in this case, the deflection is vertical and mg is vertical. So in this case, mg and the spring forces should affect the deflection. So if mg shows up in the differential equation and the differential equation is not this simple, then would you change that formula square root K over M? Well, the answer is no. So let me show you why. Here we need to measure the deflections that X or Y or whatever you call it for a spring system, a spring mass system, a vertical system, you have to measure it from static equilibrium position. If you do that, then mg's will have no effect. Really? How? Well, let me show you. So what you do is, first you hang the mass from the spring from the wall or wherever, and you let it come to static equilibrium. What happens? mg on one side tries to bring down the mass, on the other side the spring force is trying to counteract that, but initially spring force is 0, mg is not 0, so the mass comes down until mg and the spring force, which is equal to k times this delta, and delta is the static deflection, they become equal and the mass goes to static equilibrium. Now, when the object is in static equilibrium and doesn't move anymore, now what would you do? Now, from that position, you are gonna push this mass further down by x. So when you write your equation of motion for x, x is measured from this not from unstretched position, it is measured from static equilibrium position. X is measured from that point downward. So your total deflection at this point is really x plus what? Delta. So the force of the spring when you're looking at this FBD is k times x plus what? Delta. On the other hand, you also have this mg or w. So when you draw the FBD for this system that is going to oscillate, there are two forces, w and k times delta plus x. So if you write the equation of motion, sum fx equals negative k times x plus delta, assuming x positive is downward measured, and then plus mg, because mg is in the direction of x. Now if you look here, if you expand this, this is going to be negative kx plus mg minus k delta. And these two together, when you add them, they should be equal to 0. Why? Because initially, when you were in a static equilibrium, sum of these two forces was 0. So these two would cancel out, and the only thing that will left in your equation on the left side is, this two. Seems like I made a mistake. Yes, I did. It's like this. These two would cancel out. This guy stays, you take it to the other side, and you get the same ODE that you got for the horizontal mass spring, right? Look here. That's the same ODE that you had for the horizontal mass spring system. You get it now for the vertical one. If and only if, again, your measurements are taken from static equilibrium. And you might say, well, can I not start it from static equilibrium? Yes, you can. But why would you bring it to static equilibrium? Because if you don't bring it to static equilibrium, you always you want to have the system kind of be symmetric about that middle position, right? So here, if you look, when x is 0, there is no force in either direction. When you move x to the right, now you start getting a force to the left. When it comes back, passes this middle point and moves to the left, the spring force is going to be applied to the right, and you slow down, and then you go back to the right. So your force is symmetric about the midpoint. The same thing goes for the pendulum, right? This mg sine theta, which will create the moment, it depends on theta. If you are here in the middle of the oscillation, theta is 0, sine theta is 0, there will be no moment. So the torque on the left and on the right side of this oscillation will be symmetric. Okay? So here, to get a similar result, you want to bring it to a position that when you are in that position, in the start position, the system has no total force. Why? Because this initial deflection of the spring and the mg have canceled each other. Now, by forcing some initial condition, you are bringing the extra force. And that is the cause of oscillation. So in this case, if you plot the oscillation of the system, you see that it is going to be perfectly symmetric about the static equilibrium point. Okay? But if you do it about the unstretched length, that's not going to be symmetric. Okay? That's not going to be symmetric. So you get a lot more in this direction and a lot less in this direction. Okay? Or actually, it can go a little bit up in this direction as well. So you get a little bit like up here and a lot more down here. So to make it perfectly symmetric, we most of the time measure it from static equilibrium. And again, you see that the equation is as if the weights can be neglected. Good. The last problem that we are going to solve is a little bit more interesting. So here I have something like a seesaw, which is pivoted at the point of centroid. So centroid is here, distance c from the pivot. And at the two ends with distances a and b, I have two springs with constant k. And the only degree of freedom in this system is theta, this angle measurement in a clockwise manner. I want to find the equation of motion for the system and find the natural frequency, assuming this theta is what? Again, a small angle, because if it's not, you're going to get sine terms or cosine terms. So we assume small angle, and we model this seesaw as a slender bar, okay, with mass m and total length a plus b. So what would you get? You draw the FBD for it. If you draw the FBD, you have the pin forces OX and OY. There is mg here, assuming the mass is m, and there are forces from the springs. Now, what are the forces from the springs? for them, assuming that when the seesaw was horizontal, we have to find how much is the deflection now that the angle is theta. So I need to find these deflections at the two ends. And from what you know from definition of angle in radians, if this is a center and this radius is A and I rotate by angle theta, this guy here is how much? You know this is A sine theta, correct? Or A tangent theta, depending on which one you're using. Okay? But when the angle is small, whether you use sine theta or whether you use tangent theta, they can be both approximated by what? By theta itself, because the angle is small. So I can say this basically vertical distance is A times theta, on this side is B times theta. So K times A theta is the force on this side, K times B theta is the force on the other side. Now this side the spring goes down, so the spring is going to push back. This side the spring goes up, so it's going to pull back, so it's going to be downward. So that is your total FBD of this system in a situation where there is deflection by angle theta, or displacement angle theta, deflection theta really. It's not a pure displacement. Okay, so now what? Now here again, you might say, where is this theta measured at? Is this measured from horizontal position? Or is it measured from when the seesaw comes to equilibrium? Now, what does equilibrium mean? Because your centroid is not at the pivot point, this mg will create a moment about this pivot point, a clockwise moment. So even without you adding some initial deflection for theta, the initial position of the seesaw at equilibrium and static equilibrium is already a little bit tilted. Because again, your pivot point is here, your mg is there. So initially, your seesaw is not going to be perfectly horizontal to begin with. You initially have some theta static for the system to be at equilibrium. Then your theta, if you draw this seesaw again, your theta is really measured from that static one. So the way that the theta is shown is kind of misleading. Theta is really measured from the static equilibrium theta, which is a few degrees depending on how much this mg is, and it's measured from there, not from perfectly horizontal one. Okay, so in this case, this line is the horizontal line, this is the seesaw tilted, and this is the seesaw with initial extra deflection. Okay, so keep that in mind. And if that's the case, when you write sum of the moment about point O, not only these two will have moment, then mg will also have moment, but the moment of mg will be cancelled by the moment of these spring forces that initially were created by the theta static. So if I draw the FBD of the system under a static scenario, this is my system under static scenario. There is mg here. There is one force there, and there is one force here. How much are these? This is K A theta static. This is this is KB theta static. And in this case, sum of the moment about point O was 0. So basically, mg times distance c and then minus Ka theta static, that's the force, times the distance, which is A again, and then minus this force, which is Kb theta static, times the distance, which is B, that was equal to sum of the torque about point O, and it was 0 in the beginning. So in the beginning, these guys were holding an equilibrium together. They were equal to each other, okay? So this guy, the positive one, was equal to the sum of those negative ones. Now, when you move off of the equilibrium, your actual forces are not simply Kb theta and Ka theta. Really, these forces, if you want to know them, they are Kb times what? Times theta plus theta static. And this one is also going to be Ka times theta plus theta static, because that is your total angle measured from the horizontal direction. But again, this portion of it, this portion, and this portion would cancel this mg based on what I just showed you above. Therefore, we cannot include mg if we want, and those static ones, and make it a lot simpler by simply doing this FBD. Look. In this FBD, I did not show mg, and I did not show the static thetas anywhere. Why? Because I know, since I'm measuring everything from static equilibrium, I can just cancel those. And so this could be a little bit misleading if I don't explain all of those previous steps. So now that this is the case, if I take some of the moment about O, this force is multiplied by its distance, and of course, since theta is clockwise, this force is creating a counterclockwise, so it's negative. This force is also Kb theta is multiplied by this distance B, and it's also counterclockwise, so that is also negative, equals polar moment about J times theta double dot. Now, if it's a slender bar, this could be replaced by what? J about O. Well, in that case, we have to find it, and I'll show you. But if it's not a slender bar with mass m, just arbitrary seesaw, then your equation of motion is going to be this. And then this guy here, this coefficient, is going to be omega n squared. So your natural frequency in this case is square root of K A squared plus B squared over J O. Now, if it is a slender bar, J is going to be what? Because in this case, your centroid is a distance C off from point O. So J about O, if you use parallel axis theorem, is J about the centroid plus mass of it times distance squared, which is C squared. And what is for a slender bar? It's mass times length squared divided by 12. Now the length of this guy is A plus B. So I have to replace that into place of J naught, and that will give me what? Omega n. Again, if I assume the seesaw is a slender bar. If it's not, then JO has to come from the CAD model of the seesaw. But this is another example of a single DOF, free vibrations with small angle assumption and with single degree of freedom, no damping. So hopefully all of these 6 examples that I solved gave you an idea, better idea of free vibration of undamped single DOF systems. Stay tuned for next video where we add the damping, and the video after that where we add the forcing function and make it forced vibration of single DOFs. Thank you so much. I'll see you in the next lecture.